So welcome to the second part of the first day's lecture. This is for January 4th, 2016. Uh, all right, so until now, what you have seen is the syllabus for the class and things like that. In the current lecture, what I would like to do is present to you some of the history of how dynamics has been studied and why. It's hard to answer why, but we've always been captivated by moving bodies. So we'll talk a little bit about that and then bring it into the scope of the current class and talk about the kinds of problems that we might be looking at over the coming weeks. Okay, so let's get started. So the history of dynamics can be traced back to Aristotle actually. So there is something called Aristotelian physics. You can look this up on Wikipedia if you're more interested. But in his book On the Heavens, Aristotle actually has posited the possibility of the existence of the law of inertia, which was later codified by Newton many hundreds of thousands of years later, in fact, almost 1800 years later. Right. So you can see that this is where it all begins, is probably with Aristotle, at least that's what's documented, right? And then since Aristotle, we've had a bunch of other big names along the way. We've had Galileo, and Newton, Isaac Newton, right? And each one of these people, these characters, have been responsible for the development of dynamics. But there is, of course, a big gap in time between Aristotle and Galileo. But we've always been obsessed with things that move and to determine how things might move, because we always want to come up. Scientists always have this innate desire to come up with answers for why the world works the way it works. And so the foundation was laid by these people, actually, for the stuff that we do. So coming back to dynamics, dynamics is a branch of mechanics, you could say, or applied mathematics that is concerned with the study of motion and the kinds of factors that might cause motions, like forces and torques and things like that, right? So let's define what dynamics is. Dynamics is the study of the effects having some trouble with this, effects of forces and torques on the motion of bodies, right? So as of right now, we haven't really defined what forces exactly are and what torques exactly are. But if you go back and look at the syllabus, I've told you that we will be in certain weeks looking at the effects of forces, and torques will also be introduced as a concept. So if you don't remember what these things are, or you just don't know, we will come to these things again and come up with very formal definitions for what these specific terms comprise. But as you know, dynamics is now going to be the focus of our class, at least, is going to be studying the motion of bodies. We may study the motion of bodies assuming that there are already forces acting on it, or that there may or may not be any forces acting on it that may cause the motion. Maybe a body is just moving and we want to know where it goes when it's already in motion, right? So these are some of the things that we will look at, right? So given like a very brief history which begins at Aristotle, which is back in the BCs, and coming all the way through to Newton, and today we even have more proponents who've worked on dynamics, right? So if you're interested in things like motion of satellites and how we launch things into space, and like how you predict the trajectories of certain things, how you design trajectories, dynamics is still used today. So it has a very, very solid application to this day. So this can be a very, very crucial class, actually, for anyone who's interested in those fields, right? So coming back to the principles of dynamics, right? We listed the three names, but the most important of those names was actually Isaac Newton. So Sir Isaac Newton is perhaps the living legend when it comes to dynamicists and just talking about major contributions. And a lot of you must be familiar with Newton's second law of motion. So, Newton's second law of motion. This, right, this is basically everything that the course is about, right? The course is all about taking Newton's second law of motion and applying it to a body, and that will tell us what happens to a body under certain criteria. So, or criteria, I should say. Right. So, what is Newton's second law of motion? So, Newton said that a force applied to a moving body is directly proportional to its acceleration, and that proportionality constant that relates the two is through the mass of the body itself, right? So, F equals mass times acceleration. F is the force. So we will write that out. F here is the force equals this here, M is the mass, and this term here is, let's change the color for that one and take that, and this term here is the acceleration. So I'll just write that as ACCN because I have limited space. All right, so this is the crux of what these the rules that govern dynamics of moving bodies is based on, right? But there is one thing that's very important, is that right now the way this equation over here is written out, F equals m times a, does not seem to have something that we call vector notation. So we will be discussing what vectors are and things like that in the coming weeks, but for now just note that if something is a vector, I will put a tilde under it, right? So I'm going to do the same thing for acceleration. I put a little tilde under it. Of course, there are different other notations that you may use for vectors, like say some people like to write acceleration as in this form, right? Other notation for vectors is something like this, right? Take acceleration. Some people like to write it like that, some people might write it like this, but you can see that there is always some kind of identifier that accompanies the letter in the alphabet, right? Either you have a little bar that is going over the letter, or there's an arrow, or as I wrote in the case above, there is a little tilde underneath, right? So it's going to be very important to remember that when we're talking about these things, we're talking about vector equations of motion. So we'll go into detail about what vectors are in the next two lectures, which I will be sending you links to as well. And that will review vector algebra and concepts like that. Then we will take the concepts of vectors and apply that to bodies, systems of particles and bodies, right? So on that note, I have said that, and it's also in the syllabus again, we've talked about the kinds of systems that we will be looking at in especially the last 3 weeks is particles, systems of particles, and rigid bodies. So to give you a brief idea about what that entails is we can again talk about this in terms of Newton's laws, right? So coming back, we will say a particle, right, is something that has mass but no dimension. Something with mass, right? So it has a weight that you can write basically for it in newtons or something like that, mass in kilograms or pounds or anything like that. Something with mass but no defining geometric features, right? No defining geometric shape. right? So a common way that a particle P gets represented is by, let's say, so this dot here is a particle P of mass m. This is conventionally how we will be seeing a particle being defined, right? So this is the first kind of thing. So we like to write out an equation of motion for this. We apply Newton's law, and you can see that we can easily write F equals mass times acceleration, force equals mass times acceleration for this body. If there is a force acting on it, say in that direction, so that's a vector, and it causes some motion in some arbitrary direction. Let's say that it is constrained for some reason to move that way, right? So these are the kinds of things that we'll see when it's applied to a single particle, right? But in a more complex system of particles, we can have, let's say that your system is now comprised of many particles like this, right? So system of particles, right? So this is nothing but we draw some kind of loose boundary, and right, and we put a bunch of little dots, right? And we can have an infinite number of these. It depends on the kind of problem that we are solving and how many particles we might need to approximate the system. But you can call this first particle P1, right? P1. I'll call another particle here P2. I'll call, say, some particle here P3, and so on. So you can name each and every particle over here, and they may or may not have the same masses. So we'll give it some initial mass m1, some mass m2, so on and so forth, right? So just to remind us that some particle there, right? So now we would like to study the motion of not just one particle as in the case above, but a system of particles. So we have that, right? And this boundary that I've drawn over here is just an abstraction. So I'm talking about this boundary here, right? It's just some kind of abstraction that I've come up with right now, but we look at this in more detail in the coming weeks again, right? And finally, we will close with something that has a shape, right? So then we look at rigid bodies, right? So rigid body, commonly, if I'm just talking about an arbitrary shape or an arbitrary body, let me rewrite that a little clearly. Rigid bodies, right? Yeah, so we use this potato shaped or pear shaped body, and we like to name things. We always like to know what we're talking about. So in dynamics, I like to label things. I say this is a body B of some mass m, right? And I want to know how it moves around. But the thing is, in this case, the body can twist and turn, right? So let's say that I could make this body turn in a clockwise manner, right? So I'm going to say that a clockwise manner would mean that the body can turn like that. So it's going to make a clockwise rotation in the plane of the paper that you're looking at, right? And I want to know how it turns as well. So now we have an additional set of equations, and we will go into this as well in the coming weeks. And that the motion of this body is actually kind of governed by something called Euler's equations for rigid bodies. Euler's equations for rigid body motion, right? And over here we will start to look at things like torques and that kind of stuff, right? So this is kind of a sneak preview into the kind of things that we will look at in the coming weeks. Common problems that you might end up seeing might be, or at least in the class, we will look at things like, say that you have, let's take this case of a simple pendulum, right? And the orientation of this pendulum is measured with some angle, let's call it theta, right? We would like to know how this body swings around, right? So the goal of this class will essentially be to find out what kinds of forces might or might not be acting on this system, right? Identify forces, study motion. Essentially, these are the two steps, right? But this studying the motion section of things is very, very important. So when I say it's very important, I'm going to put this step here, right? So this is going to involve something called kinematics. So if you go back and look at the syllabus, I've said that the first 3 to 4 weeks after we're done with the vector algebra section, we'll be looking at kinematics. So kinematics is the study of motion without understanding forces, right? Like without looking at what force might be causing a motion. And then we can take the knowledge of what we have of kinematics and plug that in with, or couple that with the effect of the forces and see what this body is going to do eventually. So it's a systematic approach to studying how a body moves. So don't get too flustered right now. What I would recommend is just go over the lecture content again, and I will also be posting my notes online for you to look at. So if you have any questions, feel free to shoot me an email and I will respond to you as soon as I see an email, or whenever the hours are convenient and things like that. So yeah, with that, I would like to just say that I'll see you guys in the next lecture. I'll send out the link to that as well in a couple days. That will be posted precisely at 10 o'clock in the morning, so you should be able to see a good 1.5 hours to 2 hour lecture in the given time. All right. Thank you.